Hello everybody. So today we will discuss about the other connections of the three-phase transformers. Till now we have seen the connections like a star-star connection, a star-delta connection, delta-star connections, and delta-delta connections. Then we have talked about open delta connections. So today we'll talk about the other some special types of connections. Basically, Scott T connections and zigzag connections. So basically, zigzag connections is also a kind of star connections only, or delta star connections only. But Scott connections, they are used for phase conversion. That means till now the other transformers, generally what we see that we step up the voltage or we step down the voltages, and accordingly the current actually steps up or step down. But in Scott connections, in a Scott connection, it serves the same purpose, either to step up the voltage or step down the voltage. Along with it, the main function of it is it actually converts a three-phase system into a two-phase system. Earlier, there were like a lot of motors which used to work on two-phase supply actually. Okay, so there, since three-phase supply is coming, and from three-phase supply, that supply was converted to two-phase supply and it was fed to the motors there. Okay, and there are some electric arc furnaces where these two-phase supplies are required to actually to energize the arc there. So there actually we use this Scott T connections. Okay, so for Scott T connections, if you'll see, basically we need, for Scott T connections we need actually two transformers, two identical, I would say, transformers of two identical, and I would say single phase transformers of equal turn ratio. And second is, on one transformer we have a tapping at root 3 by 2. So on one transformer we have tapping at root 3 by 2 number of turns of primary side, let's say NP. So on the primary side we have actually a tapping at this number of turns. Okay, root 3 by 2 times of NP actually is required. Generally we use it for three-phase to two-phase conversion and for two-phase to three-phase conversion. But since nowadays we don't have two-phase generator, so we would say that it is more restricted for three-phase to two-phase conversion only. And we have one experiment related to Scott T connection in our lab as well. Okay, so how we do the connections here? So we have basically I said two single-phase transformers. So let's say one transformer winding, and from the dotted end at, let's say, root 3 by 2, if total number of turn is NP, if this entire number of turn is NP, and for the secondary side, if I say this entire number of turn is NS, so turn ratio NP upon NS, primary upon secondary, is actually A:1. So we need a tapping here actually at this point. So this is one single phase transformer, one unit. Okay, so we have the access to this tapping as well. But this tapping, let's say A, and this tapping point M. So this is at 80 root 3 by 2 times of NP. Okay, which will come around 86.6%. Okay, so this is used to, or this, and there is another transformer who is having where we connect at the midpoint of it. So this transformer is known as teaser transformer. And we have another transformer, and we have a tapping here at the midpoint of it. So let's say here this entire is NP, so we have a tapping here as well. And what we do is we actually connect it here. So if this is phase A, let's say we have a three-phase supply here. So phase A is connected here, and phase B is actually connected here and phase C is connected here. So this is A, this is B, and this is C. So dots are marked here for the transformer. Let's say this, I would say transformer T2, and this I will say transformer T1. And this transformer, the second one, this is known as the main transformer. So we have the dot here and we have the dot here. Okay. If this is the NP, so number of turn here is also NS. So same turn ratio. So these two are the transformers here. Okay. These two are the transformers here. For the simplicity of explaining it, and these I am actually marking it here. I have drawn in this way. Okay, but no harm in it, because this does not represent the actual transformer representation. So phase A, phase B, and phase C has been connected at the primary side of these transformer, and these are the secondary terminals. And this is the second transformer, second single phase transformer. So let's try to find the voltage, how the voltages will actually appear. Let's say, for the sake of simplicity, I am saying VAB. Earlier we used to say that, okay, phase voltage at a particular angle, then line voltages we used to calculate. Simply I am saying, okay, this line voltage is at an angle of, let's say V at an angle of positive 120 degree. VBC is at an angle of V at an angle 0. And VCA is V at an angle of minus 120 degree. So if I draw the phasor diagram for this, it would be somewhat like this for the primary side. Let's say VBC, VAB, and VCA. Or let's say how to calculate the, if we have energized this voltage here, this line voltage AB has been energized between these two windings, how the voltages will appear. Let's try to find that. Okay. So obviously this, I will take the transformer T1, the main transformer. So this is also known as, this transformer is known as main transformer, on which you have 50% of the turn ratio division there, and on which there you have 86.6% of the turn ratio. We say it as a teaser transformer. Okay, so this is teaser transformer. Let's try to find the voltage, how the voltages will appear at the secondary of these two transformers. Okay, so here you will see whatever voltage which is appearing here towards the dotted end, same voltage as per the turn ratio will appear here on the main transformer as per the turn ratio. Okay, so let's say the voltage here is VBC. So let's say these terminals are B and C here, and this terminal is, let's say, A and M here. So what about the secondary voltages here? So if you see the secondary voltage VBC upon V capital BC, and secondary voltage VBC is this side and VBC is this side, right? So this would be, as per the turn ratio, this voltage will appear here, right? So this is 1 by A, and this implies VBC is actually V at an angle 0 upon A, right? This one will put it here for VBC. Okay, so this is the voltage which is appearing here. Let's see what voltage will appear here if I take this turn ratio there. So obviously we need to first find what would be this voltage, VAM. Okay, so we need to first find VAM, and if you'll see that this would be, if you just try to find what this VAM would be. So let's try to find this. For this we'll apply a KVL here on this voltage, and let's try to find it. Okay, let's say VAM is in this direction. Okay, this is VAM. So if you write the KVL here, VAB minus VAM, and again this side you will be having the increase in voltage, right? And plus VBC by 2. They are all in phasor only. This will come out to be 0. Here Y minus VAM I have taken because there is a drop in the voltage here. Okay, so VAM, if you will see, that will come out to be VAB plus VBC by 2. So VAB is this, and let's say I'm just redrawing this phasor for the sake of understanding. So I'm just redrawing these phasors, okay, for the sake of explaining it better. So if VBC is here, VAB I can draw it here as well. VAB. And VBC would be here, right? If this and these are parallel, VAB, this one and this one are parallel. This one, they are parallel, right? So this is here and this is here. So you see here, VAM is actually VAB plus BC by 2, right? So plus BC by 2 would be somewhere here at the middle of it. Okay. So let's say BC by 2 and VAB, right? If you sum these two, the resultant would be this one at the middle of it. Okay. And if you will see that this would be actually AM, and this would be at 90 degree to it. Okay. So VAM, if you will see, this we can write as VAB. So VAB is V at an angle of 120 degree, and VBC by 2 is half of V at an angle of 0 degree. Okay. And if you will solve it, you will see that this magnitude will come out to be root 3 by 2, this one and this one. Also you can see the magnitude as well, right? If you project it, so this is 30 degree, VAB cos 30, if you see, that would be, because the magnitude of this length AM would be VAB cos 30, right? So that would be V cos 30 is root 3 by 2. Okay. And even if you solve these two, you'll get this magnitude only. VM, this at an angle of 90 degree. Okay. So VAM is 90 degree to VAM is 90 degree to VM is at 90 degree. So what would be the voltage which is appearing here? Let's say V small am, VAM, which is at the secondary side, right? This is at secondary voltage, right? Secondary voltage of teaser transformer. So this would be VAM would be, so VAM upon VAM, capital AM, if you'll see, that would be the turn ratio, right? So turn ratio is what? You can see that the turn ratio we have chosen 3 by 2 of NP, right? Or simply root 3 by NP. So this is the secondary side voltage, which is NS upon VAM, the primary side turn ratio, if you'll see, that is root 3 by 2 of NP. And this is nothing but 1 by root 3 by 2 of A, right? So VAM, if you will see, this will come out to be VAM upon root 3 by 2 of A, and if you further simplify it, you'll get V by A at an angle of 90 degree. Okay, so you see here the line voltages or the voltages on these, the secondary side, the phase voltages you say on the secondary side, two phases, they are of the same magnitude and they are displaced at an angle of 90 degree. Okay, same magnitude, V by A at 90 degree, V by A at an angle 90 degree, at VBC, this voltage was V by A at an angle 0 degree. So that's how we have converted a three-phase system, three-phase voltage to a two-phase voltage. Okay, and if you analyze the current as well during the loading condition, the current, you will see that the primary side current IA would be equal to IB would be equal to IC. Okay, so this I'm not going to verify, you can verify it. For the for balanced load at secondary side, okay, if you verify that, you will find that these currents are also balanced only and they are at 120 degree phase apart. Okay, so that's the beauty of this transformer.